Hi, this video is about trigonometric ratios. This is not a topic that's directly covered in your textbook, but it's closely related to similar triangles, and it's something you will see in other contexts quite soon, so I thought I would incorporate it. So let's suppose we have a right triangle with a 19-degree angle. All right, so I will do my best to draw something that looks like it has a 19-degree angle. And let's draw another triangle that also has a 19-degree angle, but differs in size and orientation. So I'll make this bigger and I'll twist it a little bit. So right angle at A and D. And then here is B with 19 degrees, here is E with 19 degrees, and then C and F. We know by angle that triangle ABC is similar to triangle DEF. So what that means, if we look at these fractions, AC compared to BC, AC is the shortest segment. It's the one opposite the 19-degree angle. And BC is the hypotenuse. So AC compared to BC is comparing this side that is across from the 19-degree angle to this side that's across from the right angle. And DF and EF are the same comparison in similar triangles. So these fractions would be equal. And it turns out not only are they equal, but it has been calculated exactly what that fraction is. Now, exactly how that's done is not what I'm going to get into. Theoretically, if we had very accurate instruments, a protractor that built something that was exactly 19 degrees and we measured the lengths very, very precisely, we could do it that way. There are other mathematical techniques for figuring this out. But this ratio is just known. And what this means is if we know this number, if we know this ratio, then any time we see a right triangle with a 19-degree angle, we can use it to figure out additional information. It's kind of like 30, 60, 90. In a 30, 60, 90 triangle, I'm going to draw one and then erase it. We just plain know that this short side is half as long as the hypotenuse, and that we memorize, because it's such a nice relationship and 30 degrees is such a nice angle. What we have here is a similar rule about 19-degree angles. If we have a triangle with a 19-degree angle and a 71-degree angle and a 90-degree angle, there would be a similar rule, it's just not as elegant. So if I had a triangle like so, a right triangle, where here's my 19-degree angle and my hypotenuse is 20. Well, I know that this triangle is similar to the ones that we saw before. So this ratio would be the same as this number. And I could multiply both sides by 20, and x would be approximately 6.5. I don't have my calculator handy, but I'll do other problems with a calculator in a second. But the point is, we can figure out how long this side is because we know what the ratio is. So what we saw here really is not about any particular triangle. It's just kind of a property of what happens when we have a 19-degree angle in the context of a right triangle. And we could do that with any acute angle. Right? I told you what the number is when we have a 19-degree angle. If we had a 53-degree angle, that number is known as well. So here is what we're actually going to define. We're going to define a ratio called sine. So let's suppose we have a right triangle. Here's our right triangle, and here's an angle called theta. This is the Greek letter theta, and it's very often used in trigonometric examples as kind of a variable that stands for an angle, or an angle measure. So the sine of theta, that's abbreviated sin theta, is the ratio between the length of the leg that is opposite theta. I'm not going to say, oh, the big leg or the small leg or the top side or the bottom side or the left side or the right side. Instead, I'm going to think, how is it related to this angle? We'll look at the leg all the way across from the specific angle theta. That we would call that the opposite leg. So this is our opposite leg. This side here is our hypotenuse. And the sine of theta is simply the ratio between that opposite leg to the hypotenuse in any triangle that has a right angle and an angle of theta, because they would all be similar to each other. And these values of sine are just known. You are not going to have to figure them out. You can look them up in tables. You could just do a Google search. It's built into your calculator. So you'll have to see how to do that. But the point is, once you understand that there is this thing called sine and you can just ask your calculator for it, then these problems become very doable. So draw a triangle with a 67-degree angle. Draw a right triangle with a 67-degree angle and a hypotenuse of 8. Calculate sine of 67 degrees and use that to figure out something else in the triangle. So hit pause. Okay, I hope you have done this. So I will draw a picture, and I will do my best to draw an angle that looks at least plausibly 67 degrees. I feel like that's not so bad. Here's my right angle. Here's my 67-degree angle. And we're told that the hypotenuse is 8. I'll call this A and this B. So sine of 67 degrees is a ratio between the opposite leg, across from the 67-degree angle. That's A. It's the ratio of opposite leg, which in this picture is A, to the hypotenuse, which is B. And then sine of 67 degrees I can just look up. So, oops, let me see if I can split my screen. So I have Wolfram Alpha, which is a website that does all kinds of math stuff. I just don't have my calculator handy right now. But I could just ask, what is sine of 67 degrees? If you ever do a Google search, make sure you include the word degrees. So sine of 67 degrees, and there it is, to a ridiculous number of decimal places. We'll round this to just 0.9205. So 0.9205 is equal to A over 8. So then if we want to know what A is, we can multiply by 8. 8 times 0.9205. So I think I could actually just type times 8. Probably should have found my calculator before I started this video. And it's approximately 7.364. There's a little bit of rounding, but there's a super accurate answer if you want it. So I'll hide this for now. We didn't have to have this memorized. We just needed to understand that built into our calculator or looking it up online, the values of sine are known, so we can use that and a little bit of math to figure out another side in this right triangle. Sine is an example of what's called a trigonometric ratio. Trigonometry encompasses a lot of different ideas related to angles and circles and measurements. We're just seeing a very tiny portion. And sine is not the only trigonometric ratio. There are other well-known ratios that tell us how different sides of a right triangle are related. So for example, there's one called cosine of theta. That's abbreviated COS. So I'll draw a right triangle. Let's suppose here's theta. Cosine of theta is the ratio between the adjacent leg, the leg of this right triangle that appears to be right next to, right, that lines up with the angle theta. We're always talking about this from the point of view of the angle. So if we're thinking about this angle here in the lower left corner, then this side is the adjacent leg. But if the picture looked different, if my picture looked like this, then right here is the adjacent leg. So don't get caught up on, is it big, is it small, is it top, is it bottom? You really need to think about where is it compared to the angle. Cosine is the ratio between adjacent leg and hypotenuse. So sine compares opposite leg to hypotenuse. Cosine compares adjacent leg to hypotenuse. And there's a third one we'll talk about here called tangent. Tangent of theta compares the opposite leg to the adjacent leg. Oops. So I'll change the orientation. Here's my right angle, here's theta. So this would be the opposite leg. From the point of view of theta, it's the one that is across from it. This would be the adjacent leg, in this case at the bottom. And tangent of theta computes the ratio between those two sides. In any triangle with the same angle theta, that ratio would be the same because the triangles are similar, assuming they are right triangles. And all of these are programmed into calculators and are easily looked at. Sine values, cosine values, tangent values, any scientific or graphing calculator has them, so it's very easy for you to find those numbers and use them to solve problems. Now, it's very easy to forget which one is which. So there's this 9-letter nonsense word called SOHCAHTOA that people like to just say to remind themselves of what's what. So the idea is you look at it 3 letters at a time. SOH, the so, is basically an abbreviation for sine is opposite over hypotenuse, SOH. The CA, the CAH, is cosine is adjacent over hypotenuse, CAH. And finally, the TOA, oops, I wanted to highlight that. The TOA is TOA. Tangent is opposite over adjacent. So you can use these. Whenever you have a right triangle, if you know one of the acute angles and one of the sides, you can figure out everything else. You identify which acute angle is the important one, and then you figure out what sides you're thinking about from the perspective of that angle. Which side are you given? Which side are you trying to figure out? Is it an adjacent leg? Is it an opposite leg? Is it a hypotenuse? And that's always in terms of where it is compared to theta. You calculate the appropriate sine ratio, and then you solve. And the appropriate sine ratio will be based upon the combination you have. So let's do a couple of quick examples. So suppose I have a right triangle like so. So let's put the hypotenuse actually at the bottom. And so here's our right angle. And let's suppose that I say this is 6 and this is an 81-degree angle, and I want to find x. So from the point of view of the 81-degree angle, this is the adjacent leg. This is the hypotenuse. So we ask ourselves, which one uses adjacent and hypotenuse? Which one uses A and H? So SOHCAHTOA, it would be cosine. So cosine of 81 degrees would be 6 over x. I want to solve for x. So I want to get rid of this fraction. Let's multiply both sides by x. So times x, we would have x times cosine of 81 degrees equals 6. X is 6 divided by cosine of 81 degrees. And I can get that from the calculator. Let's just, there we go. So we want 6 divided by 6 divided by cosine of 81 degrees. It's a little awkward that I'm typing this rather than doing it on a calculator. And this works out to be about 38.355. So my picture here was not perfectly accurate. I think this is not close enough to 81 degrees. But certainly x is substantially longer than 6. That's supposed to be true. We can also have word problems that use trig. And I'll give you one that's actually similar to what people would do in real life. I'm oversimplifying a little bit. But what if we had a very tall tree? Do I have, let's find green. All right, so green. Suppose we have a very tall tree and we want to know how tall this tree is. Right, now, theoretically, you could climb to the top with a tape measure and then drop the tape measure, but that seems dangerous and very difficult. So instead, there's very accurate equipment that can be used to figure out angles when you're at a distance. So what you could do, for example, is you could walk a certain distance away from the base of the tree. Suppose you walk 300 feet away. And you set up here with some technical equipment, and you point a lens towards the top of the tree. And then the machine will measure what that angle is. How much did we have to tilt upwards so that we're pointed exactly at the top of that tree? And let's suppose that it is calculated that that is 38 degrees. Well, we could use that to figure out the height of the tree, because we basically have a right triangle in this picture, right? The tree presumably grows straight up. So that's perpendicular to the ground. Here's 38 degrees. From the point of view of 38 degrees, this is the adjacent leg. This is the opposite leg. So those are related by tangent. Tangent of 38 degrees would be t over 300. So t would be 300 times tangent of 38 degrees. And we get a number for that. 300 times tangent of 38 degrees. So 300 times tangent 38 degrees. And this works out to be approximately, where is it? 234.386. 234.386. And this is a word problem. The units there are feet. So there we go. You'll have some homework to practice on, but this video gives you the basics.